All right, so now we're going to talk about arguably the most important application in this class. And that's the idea of applied optimization. So the idea is really simple. You have a real world problem that can be modeled by a function, and your goal is to either maximize or minimize that function. And in doing so, you're going to be optimizing or maximizing or minimizing some real physical quantity. This happens all the time. So like I said, this is called applied optimization. And the general idea behind applied optimization is this. We want to maximize or minimize a function subject to some constraints. So let me just tell you a couple of maybe like really big picture applications here. So maybe f of x is a profit function and x is the number of units sold. Okay, so maybe you're selling something, you're trying to figure out how many do I need to sell to maximize my profit. Okay, and of course, the silly thing would be, okay, well, if I sell, an arbitrarily large amount, my profit will get arbitrarily large. But in reality, that's where constraints come in. So I can't just typically make my function I want to maximize or minimize. Sometimes this function is called the objective function, just for some terminology, the function you're trying to maximize or minimize. So most of the time, it's not possible to just make your objective function arbitrarily large or arbitrarily small, because you're going to have some constraints. So in the example of our objective function being, say, a profit function, our constraints is that, well, it would be great if I could sell an arbitrary amount of whatever I'm trying to sell of products. But the constraint is that maybe I don't have that many people that will buy them. Or maybe it takes a lot of money to produce a certain amount. And maybe there's kind of an optimal amount that I want to sell that's going to allow me to maximize my profit. So I always got to consider my constraints. But this is the general setup of what we're going for. We have an objective function that we want to maximize or minimize subject to constraints. Okay, so these optimization problems, there's a lot of connection with what we did with related rates. They're very similar in that the problem is typically just going to be a word problem. It's just going to describe the situation to you, and you're going to have to infer or pick out what you're really trying to do. Okay, so this is why optimization problems are often considered some of the hardest problems in calculus, is because, well, first of all, there are just so many steps, okay? Even though the idea is pretty simple, in practice, each problem has its own language, has its own strategy, but there is kind of a general strategy for these optimization problems, just like we kind of had a general strategy for related rates. So the first step that I like to do is to draw a picture, label the picture with the relevant variables. Again, that process of just extracting information from the word problem so that I don't have to read the word problem more than just a couple times at the beginning to do this extraction. Then with optimization, it is essential that you identify the objective function. You need to find the quantity that you're trying to maximize or minimize. If that quantity is volume or profit or time, whatever it is, you need to explicitly state, this is the objective function. I want to minimize this. I want to maximize this. Once you have the objective function, the next step is to list the constraints on the objective function. Because a lot of times you'll have the objective function, and if it's unconstrained, it will be pretty clear that you could just do something silly, right? And just either make it arbitrarily large or arbitrarily small without considering the constraints or ignoring the constraints. So listing out the constraints show you, okay, this is what I have to make sure I obey when I'm optimizing or maximizing or minimizing my objective function. And then next is to apply the constraints to the objective function. So you're going to take the objective function and the constraints, you're going to cook them up in such a way so that you have a single function of one variable with a very specific domain. And now, in this case, the domain represents the real world constrained domain, okay? You can't have a negative area, you can't have a negative side length, you can't have you can't produce a negative number of products, etc. So there's going to be a very clear domain that makes physical sense. And now this is kind of the last step in converting this word problem into a pure calculus problem. The last step is just use calculus. And in fact, step 5 is something that we've done several times. Now, if your domain is a closed interval or it's open interval, you can use the closed interval method and the open interval method. You're going to be finding critical points. You just want to find the absolute maximum and absolute minimum of the function. Okay, so that's kind of the general strategy. I think the best way to get your feet wet is just to jump right in. So let's look at some examples. All right, so our first example, pretty classic, pretty simple, but it's going to illustrate the main ideas. So I'll give you just a minute to read the problem. Okay, and you'll notice that I've done step 1 for you here. So here's kind of a very simple picture. I mean, we're not going, for full marks in our artistic ability. We just want kind of a schematic drawing of what's going on. Here's our rectangular field. Now it's a rectangle, so it has 2 dimensions. So I just labeled one of the dimensions of the field X and then the other Y. Okay, and then let's just keep reading. So we don't have a side of the fence along the river. And here we go. What dimensions will maximize the area? Okay, so what does that mean my objective function is? I'm trying to maximize, area. We're trying to maximize the area. So I want to maximize, so here I'm just stating my objective function, maximize A equals X times Y, the area of the field, where X is sort of this length coming out from the river, Y is the length going along the river, so the area is X times Y. And here's where, you can really see that if I don't have any constraints, then this is kind of a silly question because I'm just trying to maximize X times Y. Well, why don't I just make X 1,000,000 and Y 1,000,000, or X 1,000,000,000 and Y 1,000,000,000? Just make X and Y as big as possible, and my area will just keep getting bigger and bigger and bigger without bound. Well, what's the realistic problem with that? This is where the constraints come in. So what am I constrained by? Of course, my materials. I don't have an unlimited amount of fencing. I'm constrained by my 2,400 feet of fence, or in other words, length of fence is 2,400 feet. But now what I really want to do is put that in kind of a mathematical statement. So if I'm going to use all 2,400 feet of this fence, it's going to go along these three sides. Now this is where it's significant that I don't have the fourth side. So in other words, whatever x is and whatever y is, it better be the case that 2 times x, so x plus x, those two sides, plus y, so plus this side, equals 2,400. Okay, so this is like my constraint equation right here. So constraint equation. Just to remind you, this is my objective function, what I'm trying to maximize. Okay, so I'm just trying to follow step by step these general guidelines. And we're through the first three. Notice that labeling the picture made it pretty easy to just say, okay, my area I'm trying to maximize is x times y because I have variables labeled. And then the constraint is also easy to extract from the problem. So this 2,400 feet. And I can just use that by saying exactly what that constraint is saying in terms of my variables. So everything's going pretty well so far. Now remember that step 4 is the crucial step. It's converting this sort of more or less abstract optimization problem that we have set up nicely into a purely calculus problem. And what we want to do is we want to apply the constraint to the objective function to get a function of one variable with a specified domain. Okay, so notice that here I can write this as y is equal to 2,400 minus 2x. So I can solve for one of the variables in terms of the other and then substitute in what y is. So in other words, I want to maximize the function a of x, now of one variable, is x times 2,400 minus 2x. Or if I kind of distribute this out, 2,400x minus 2x squared. Okay, so I'm almost done, but I need to understand the domain of this function. Okay, so x here is this distance. Now certainly x must be greater than or equal to 0, right? It doesn't make sense to have a negative area or a negative side length for one of the sides of my fence. And it better also be the case that y is greater than or equal to 0. So here I'm just applying some very simple realistic observations that yeah, x and y better not be negative because that is not going to make sense. But remember, y is 2,400 minus 2x. So in other words, 2,400 minus 2x needs to be greater than or equal to 0, or 2x should be less than or equal to 2,400. And of course, this just means that x is less than or equal to 1,200. So actually my domain here, x can be anywhere between 0 and 1,200 feet. If x is 0, then my fence just lies along the river, okay? Of course, there's going to be 0 area. And if x is equal to 1,200, then actually my fenced in area is just a really skinny area sticking out from the river. There's no width to it. Okay, so that's sort of like my bounding points or my endpoints, where I would expect the maximum area would be somewhere in between. Okay, so everything looks good, steps 1 through 4. Okay, we applied the constraints, we got a function of one variable, 2400x minus 2x squared, and it's defined on this closed interval. Well, here's where we can use calculus. We have a closed interval, continuous function defined on that closed interval. We know that the critical points give us the potential absolute maxima and absolute minima. So if I take the derivative and set it equal to 0, so that's going to be 2400 minus 4x. And if I set a prime to be 0, well, what do I get? I get that x is equal to 600 feet. Okay, so I have one critical point. Now I know that my absolute maximum is either going to occur at a critical point or at one of the two endpoints of my interval. So x equals 0, x equals 600, or x equals 1200. But x equals 0 and x equals 1200 are ridiculous, right? Both of them are going to give me an area of 0. Those are going to be my minimizers, right? Those x values are going to give me my absolute minimum area that I can enclose, which of course is 0. That makes sense. So that means my absolute maximum is going to come when x is equal to 600 feet. So x equals 600 feet is one of my dimensions. And then what about y? Well, y will be 2400 minus 2 times 600, which is 1200 feet. So these are the dimensions that will maximize the area of my field. Okay, so the process is really important. We set up the kind of abstract optimization problem. We convert it to in this case, a closed interval optimization problem. Okay, we know the absolute maximum is going to occur either at a critical point or the endpoints. Just based on the situation, we know that x equals 0 or x equals 1200 is not going to be the maximum, because that's kind of the limiting cases that really, are not practical. It would be kind of silly to put all your fence along the river and say, oh, that should be the maximum. Well, of course not, because that's not going to enclose any area. So the only meaningful critical point we need to test is 600, so we know that that will maximize the area. And then when x is 600, y is 1200, those are the dimensions that will maximize the area of the field. Okay, so here's another example of a typical optimization problem. So I'll give you a minute to read it. Okay, so as you can see, this is a pretty practical problem. Now I'm sure you've seen different can designs for beverages. Some of them are kind of tall and skinny. Some of them are, more, I don't know how to describe it, less tall and skinny. There's kind of a wide variety of cylindrical cans. And so, a lot of those designs are for aesthetic reasons, but we're interested here, what are the dimensions that will minimize the cost of manufacturing each can? Well, think about what that means for a second. If we want to minimize the cost of manufacturing each can, what that means is we probably want to minimize the amount of materials we use per can. And how do we know how much material we need for each can? Well, that's really just the surface area of the can, right? If we minimize the surface area per can, over a long period of time, we'll reduce the amount of, if this is aluminum, amount of aluminum or whatever metal, sheet metal we're using to build, whatever these cans are. Okay, so we want to minimize the amount of materials we use. We want to minimize the surface area per can. So that's our objective function. We want to minimize the surface area. And notice that I already drew the picture, okay? And, I reminded you, so the volume of a can, of a cylinder, is pi r squared h. The surface area is 2 pi r squared plus 2 pi RH. So here S is surface area. And it's not too hard to see where the surface area is coming from. The 2 pi r squared is the top and the bottom. Each one has area pi r squared, so we just add those together. And then the outside of the can is really just a rectangle, right? So if you think about kind of the outer shell of a cylinder, it's just a rectangle that you fold into a circle. If you don't believe me, just take a piece of paper. And the dimensions of that rectangle are the height times the circumference of the circle. So it's 2 pi r times h. So that's the function we want to minimize. Okay, and again, let's just think about the silly thing we can do. We want to minimize the surface area of a can. Why don't we just set the radius to be 0? Why don't we just use 0 materials to make our can? Well, that's of course ridiculous because I have a constraint, right? I can't just make my can have 0 surface area because then it'll have 0 volume and it won't hold any soda. But I'm constrained, I'm required to make my can have a volume of 1,000 centimeters cubed. So in other words, subject to my constraint, that the volume, so V here is volume, is 1,000, right? But what is the volume of the can in terms of the dimensions I have labeled here? The radius, r, and the height, h. Well, I have it right here. It's pi r squared times h, base times height. Okay, so I have my objective function, the surface area. That's what I'm trying to minimize. Again, from the language, we'll minimize the cost, but remember cost really refers to surface area, materials we're using. And then subject to this constraint, that the volume be 1,000 centimeters cubed. So we have objective function, and constraint. Alrighty, great. So now let's solve our constraint equation for one of the variables and then plug that into our objective function, the surface area, to get a function of one variable. So if I just divide by pi r squared, I'll get that h should be 1,000 over pi r squared. Okay, and let's plug that in. So now we have S of r is equal to 2 pi r squared times, if I plug this in for h, okay, I have 2 times 1,000. The pi's will cancel. One of the r's will cancel. I'm left with 2,000 over just r. Okay, so that's my surface area just as a function of the radius. And I don't need the height because the height will be determined from the radius based on this condition that the cylinder hold 1,000 centimeters cubed. Now what about the domain for r? Now of course r needs to be positive for sure, but can r be 0? Well actually no, because if r is equal to 0, then the volume's equal to 0. And if the volume's 0, then that violates this constraint. So my domain here is really just that r, of course, needs to be positive, but it can't be 0. Okay? Excellent. But I can actually go ahead and rule out the r equals 0 and r equals infinity case, because if r gets really small, this term is going to go to infinity, and if r gets really big, this term is going to go to infinity. So really we see that our minimum value should occur in an r, strictly between 0 and infinity. So our hope here is that we just get exactly one critical point, because if we get exactly one critical point, because we're going off to infinity on either sides of our domain, which is an open interval, that critical point will have to be the minimum. Okay? And I believe that's what's going to happen. So if we take the derivative, s prime of r, that's going to be 4 pi r, and then minus 2,000 over r squared, and we set s prime equal to 0. So these two quantities then need to be equal, so 4 pi r equals 2,000 over r squared, or in other words, if we just cross multiply and divide, r cubed should be 2,000 over 4 pi. All right. And of course, 2,000 over 4, that's just 500, so 500 over pi. And then when we take the cube root, we're going to get only one value. Okay, if it was r squared, we would have two values. Now one of them would be negative. That would make sense. But here we're really just getting one real answer, and that's the cube root of 500 over pi. Okay, and by our argument before, this has to be where the minimum occurs because it's the only critical point. And I know I'm going off to infinity in either direction of my endpoints. So again, the limit, so I'll just say s goes to infinity as r goes to 0 from the right and r goes to infinity. So here's sort of my calculus justification for why this has to be where the minimum cost occurs, or the minimum surface area occurs, hence the minimum cost. And now I need my dimensions, so what is the height? Well, once I know the radius, I know the height. The height is just going to be 1,000 over pi times 500 over pi. So cube root, but squared, so that's going to be raised to the 2/3 power. And now in terms of units, the volume was in centimeters cubed. Right, so this is centimeters cubed, which means the dimensions will be in centimeters. Okay, so of course what I probably want to do is plug these values into a calculator and actually get something that is meaningful. But once I have those dimensions, that's exactly how big you want the can to be in order to minimize the cost. Now, it's another question entirely about whether those dimensions make the can most visually appealing. Probably not, I don't know. But it's an interesting question to think about. So there you go. Okay, so another really cool optimization problem, really classic, but it's a little tricky. But first of all, I'm going to let you have just a second to read it. So I think the hardest part of this problem is actually visualizing it. And when I teach this to my students, I'll actually bring in a piece of cardboard into class and have them make the cuts. So cut these squares out of the corner. So this was the original piece of cardboard out here. Cut these squares and then fold up, and you see, okay, yeah, it is a box without a lid. It's like a shoe box that you take the top off of. Okay, cool. So, it's very important to understand that, okay, you're making cuts out of the corners, and I'm saying that I'm making a cut of length x. So I'm cutting out a corner that's x by x from each corner. And then the other two dimensions I'm just calling y and z, so that when I fold up the box, the volume of the box is just x times y times z. And hopefully this color kind of helps you see the folding. So I'm going to fold along these dashed lines. And if you're having trouble, I actually encourage you to get a piece of cardboard and do this. But you see that this red edge folds up to be right there. So this is the open top. These two blue edges get folded together, so they really just become this single blue edge. And then this green edge right here gets folded up to be right there. Okay, so hopefully you can visualize that. That's the key part. So everything's labeled here. So what is our objective function? Well, here it is. I mean, you're kind of like with related rates, there were some keywords. Well, there's some keywords with optimization. Maximum, minimum, maximize, minimize. Pretty straightforward. We want to maximize the volume. So our objective function is the volume. X times y times z, where again, v here is the volume, and then x, y, and z are just these dimensions. So what's our constraint? So again, if I wanted to maximize the volume of a box, why not just make the three dimensions arbitrarily large? Well, of course, I can't make x, y, and z as large as I want because I only have a 10 by 15 inch rectangular piece of cardboard to make the box from. So there's definitely a constraint between x, y, and z. Okay? So now, let's look at y here and z. So y, if I think about, okay, this is also x right here, and this is also x right here. If I take x plus y plus x, I should get 10 inches, right? Because that's what I'm making the box from. One of the sides is 10 inches. So in other words, 2x plus y is 10. Similarly over here, if I take z and I add this x dimension and I add this x dimension, so z plus 2x should be what? It should be 15, the other dimension of the piece of cardboard. Okay, so here are my constraints. Here's my objective function. I can get my objective function in terms of one variable by just solving for y and z. So y is 10 minus 2x, and then z is 15 minus 2x. So in other words, my volume, just as a function of x, is of course x times y, which is 10 minus 2x, times z, which is 15 minus 2x. Alrighty? So what about my domain? Well, of course, x needs to be greater than or equal to 0, but so do the other dimensions, y and z. But to say that y is greater than or equal to 0 is to say that 10 minus 2x is greater than or equal to 0. Or in other words, x better be less than or equal to 5. Same thing for z greater than or equal to 0. We have 15 minus 2x should be greater than or equal to 0, or x should be less than or equal to 7.5. So I have that x needs to be greater than or equal to 0, and x needs to be less than or equal to 5, and x needs to be less than or equal to 7.5. So because I need all of these conditions to be true, I need to intersect them, and I see that x should be between 0 and 5. And if you want to visualize this in the problem, well, look at the shorter dimension. Think about the largest cut x I could make into the corner of this 10 by 15 piece of cardboard. Well, I'm going to reach the middle of the piece of cardboard along the 10-inch side before the 15-inch side, so I can make a cut here and here of length 5 and still make like a meaningful cut. I'm not cutting into nothingness, so to speak. So really x should be between 0 and 5. 5 is the largest cut I can make and still have a somewhat meaningful box. And so notice again that v of 0 will be 0 and v of 5 will be 0. Okay, so what that means, since I'm trying to maximize the volume, is that the maximum is not going to occur at an endpoint. It really will occur at a critical point inside my interval. Okay, so the hope is I just have exactly one critical point. If I have one critical point, then everything is great. Okay, so let's first actually expand this out, make it a little bit easier to take the derivative. So our function should be, okay, this is going to be, looks like 150, 10 times 15, 150, and then we have a factor of x. Then we have minus 20x minus 30x, so that's minus, let's see, 20, 30, minus 50 x squared. Okay, and then let's see, plus 4x squared. Sorry, 4x cubed. Because we get a 4x squared times x, 4x cubed. And so the derivative is 150 minus 100x plus 12x squared. Alrighty. So let's set v prime equal to 0. Now this is a quadratic, and so we could try to factor it, but unfortunately it's not going to factor. And that's just kind of real life. Things don't always work out so nice. But we can always use the quadratic formula. And if we use the quadratic formula, we get that x is equal to 5 over 6 times 5 plus or minus the square root of 7. Okay? And then you just compute these numbers, and if you take 5 plus square root of 7 and multiply by 5/6, that's going to be larger than 5. So the only feasible solution, so the only x value or dimension that's contained in the domain that we're interested in, that's going to give us a real box, is x equals 5 over 6 times 5 minus square root of 7. So that's the x value, or the dimension, x dimension, that's going to give us actually the maximum volume. Okay. So now notice here that the question did not ask for the dimensions of the largest box. It asked for actually the maximum volume. So the answer we need is the volume function evaluated at the point that we now know gives us the maximum volume. Okay, and you just plug it in, and I'll just say you get approximately 132.038, and then units. So our dimensions were in inches, so our volume will be in inches cubed. Okay, so that's the maximum volume. All right, so this is a pretty interesting question, and it really illustrates where constraints can come from and how, something like a demand for a product can actually act itself as a constraint. But first, let me give you a minute to read the problem. All right, so the first thing I'll say is that if you're like me, maybe you never knew what MSRP stood for. Well, when I wrote this problem, I learned that it stands for Manufacturer's Suggested Retail Price. Now you know. Okay, so first thing I'll say is that it's very difficult to draw a picture here because, revenue is not actually a physical object that you can draw like a box. So what I did do is create a table. Okay, so I'll say that R here, this is revenue. And this table of values is really nice. Okay, so I just use the information. So you start with selling, so P here is price. So of course price per car. And then X is just the number of cars sold. So at $100,000, the dealership finds they're selling 20 cars per week. And then of course, the important thing to know is that the revenue, so we want to maximize the revenue. So what I'm using to finish kind of filling out this table is that the revenue is the price per car times the number of cars sold. Of course, that's what we're trying to maximize. And so if I know that $100,000 per car, I sell 20, I make $2 million in revenue. Easy. Okay, so then you start saying, well, why don't I just increase the price to $200,000? Well, now we're seeing where the constraint is going to come in. If you raise the price too much, the demand for the car is going to go down. It's going to be too expensive. But if you make the price of the car too low, then now your demand is going to go way up, but at some point you're not going to be making that much revenue, right? If you just think in the extreme, if you just gave the cars away, you would probably give away a lot of cars, but you would not make a lot of revenue. So you're seeing kind of the general situation where optimization techniques apply, where you sort of have two extremes that are bad. So what is the best thing going on in the middle? Excellent. So what is the constraint? I guess that is the next question. So subject to what? Well, it has to do with this fact, this market survey, that for each 5,000 taken off the MSRP, the dealership would be able to sell an additional 5 cars. Okay. Now this is a linear relationship, right? And it's actually illustrated here. You see that if the price goes down by $5,000, then the number of cars sold goes up by 5. Okay? So we can actually just take two of these data points. Let's just do 100,000 and 95,000 and do a simple point slope calculation. So we know that the slope is going to be, we'll just take 100,000 minus 95,000. So change in price. Let's actually do the change in cars sold on top. Okay, so 25 minus 20. Okay, so change in X, number of cars sold, over change in price, and you'll see why I'm doing that in a second. So 95,000 minus 100,000, that's negative 5,000. Okay, so it's 5 over negative 5,000, so negative 0.001 is the slope of this line. Okay, so per, I guess you can say per dollar you change per car, you'll sell, you decrease the price by that much, you're going to sell 0.001 car approximately. That's what that means. And we can just use any old data point. We'll just use the first one and then just do some point slope. And you get something like X is equal to negative 0.001 P plus 120. Okay, looks good. So in other words, this is the number of cars that would be sold as a function of price. So that is our constraint. X equals negative 0.001 P plus 120. So this is just some basic pre-calculus. You have a table of values. You have a linear relationship between price and the number of cars you'll sell. You just use point slope form. Bam. You find the constraint, right? So you see if you make the price arbitrarily large, eventually you'll be selling 0 cars. And that is the problem. That is the constraint. And now, of course, we see to get the revenue as a function of, well, we want it as a function of price, right? Because we want to know the maximum revenue, what price would maximize the revenue. So the revenue as a function of the price is P times negative 0.001 P plus 120, which is 120 p minus 0.001 p squared. All right. So now what about the domain? Well, the domain for the price, so we'll say that $100,000 is kind of the maximum you want to sell the car for. That's the MSRP. And of course, the minimum, I mean, just a silly thing to say, right? You can't sell a car for a negative amount of money. So we'll say that the minimum is 0. So in other words, P is just somewhere between 0 and 100,000. Okay. So let's take the derivative. Okay, r prime of p is going to be 120 minus 0.002p. And if we set r prime equal to 0, well, if p is 6, we're going to get 0.0120, and it looks like we just need to multiply that by about 10,000. So let's see, to get up to 120. So it looks like P should be 60,000 is our critical point. And now all we need to do is test R of, well, we know that R of 0 is 0. That's silly. We know that R of 100,000 is 2 million. What's R of 60,000? Well, R of 60,000 is 3.6 million. So actually, we see that this critical point, just using the closed interval method, of course this is in dollars, is going to give us the maximum revenue.